Good afternoon, everyone. First of all, I hope all of you had a very good Christmas break. We wish you a Happy New Year as well. Uh, and then welcome to our 19th edition of our INFOGEST Viva webinar, actually the first of this year. My name is Hernandez Olivas, and I would like to introduce Cynthia Fontes, who will conduct the webinar with me. This event is being organized by a team of postdoc from Teagasc Food Research Center in Ireland. This webinar aims to share the latest findings in digestion with presentation from the most recently graduated PhDs, postdocs, and young researchers. This webinar is being broadcasted live on YouTube and will be accessible afterwards on the INFOGEST YouTube channel. So the presentation, this time in a pre-recorded video, will be followed by a Q&A section with the speakers. So I actively invite you to use the button around here for your questions. Our speaker today is Dr. Haroon Qazi with the food structure modification in the gastrointestinal environment and its impact on the delivery of lipophilic bioactive compounds. Dr. Haroon Qazi is a researcher in food technology with a PhD from Riddet University, New Zealand, specializing in encapsulated bioactive compounds and their impact on digestion. He is currently affiliated to the Department of Food Science and Human Nutrition in the University of Veterinary and Animal Science in Pakistan, and he has extensive experience in academia and industry as well. So Dr. Qazi research combines his expertise on dairy technology and food science. His recent work explores the integration of advanced food matrices and nanoemulsions to enhance nutritional outcomes. So welcome, Haroon, and we're happy to have you here. And then, Haroon, the floor is yours.
Thank you so much. Hi, everyone. As I've been introduced, thanks for the lovely introduction. So most of the things have already been explained. I have completed my PhD last year in 2024 from Massey University Reed Institute. So my major focus was about functional foods and functional foods that are fortified with the nano-encapsulated bioactive compounds, and we use some human gastric simulator, it's a dynamic gastric model. We wanted to see how the dynamic disintegration of food matrix basically impact on the release of those bioactive compounds in the small intestine, and further, that will impact on the bioaccessibility and bioavailability. Hopefully, you can go through my recorded presentation, and definitely I will love to answer your question.
Hi, I am Dr. Haroon. I am recently working as a senior lecturer at the Department of Food Science and Human Nutrition, University of Veterinary and Animal Sciences, Pakistan. I have recently completed my PhD at the Riddet Institute, Massey University, New Zealand. My research focuses on the delivery of bioactive compound within food matrices, specifically exploring how encapsulated compound like curcumin interacts within the food matrices during the processing and further during the digestion. Today, I am excited to share my work using the INFOGEST platform. During my PhD, I worked with different food systems like the combined milk system that was prepared from differently heat-treated skim milk powders, dairy gels that were acid and rennet coagulated, and further starch gels that were prepared from the starches having different amylose to amylopectin ratio. Today, I will be primarily discussing the impact of dairy and starch-based gels on curcumin bioaccessibility. Starting with introduction, in the recent year, functional food products are in demand because they not only provide great nutrition but can also be a convenient vehicle to deliver health benefit beyond basic nutrition. Functional food. In functional food, food matrices are commonly used to deliver various bioactive compounds with the food matrix serving as a base for their incorporation and effectiveness. Among various bioactive compounds, taking curcumin as an example, whose significance on human health is well known, but its physiochemical characteristics such as low water solubility, high sensitivity to processing, and low bioavailability usually limits its utilization. To overcome the limiting factor, a delivery system is required. Thus, delivery system like oil in water nanoemulsion can improve curcumin stability, and they are efficient, and their smaller size enhances the bioavailability and bioaccessibility of the curcumin. In food matrices type on the digestion is very important to understand. So especially when we are trying to fortify any food matrix with the encapsulated bioactive compound, all of them they have a different interaction. Further, when they are processed into different structures like liquid, semi-solids or solid, they entrap the bioactive compound into different dimensions. Further, when they are consumed, especially in the mouth, in the stomach and intestine, they break down into different structures, and their disintegration, also their structures are influenced by the disintegration pattern, and which the structure basically allow, if they are very dense, they will not allow much enzyme to penetrate inside, while if they are very open, they will allow more enzyme and the fluids, the simulated fluid to enter inside uh, their food structures. So, starting with our first topic, the digestion of dairy gels, like milk can be structurally transformed into yogurt and cheese. Both of them have different distinct textural properties. Yogurt is manufactured by the acid coagulation, either by starter culture or we can add the GDL. And the cheese can be made by enzymatic coagulation using animal and microbial rennet. So, what was our experimental approach? Initially, first we prepared the curcumin nanoemulsion. We used sodium caseinate 1% and the all solubilizing curcumin, and we shear mixed them and we homogenized them to prepare curcumin nanoemulsion. Further, this curcumin nanoemulsion was mixed with skimmel powder and water to prepare our recombined milk, and further these recombined milk having the same concentration of curcumin emulsion and powder were further calculated using GTL to prepare ester gel and rennet to produce rennet gel. Our search objective was that we aim to see how different structural modification of milk protein by acid and rennet coagulation can alter the digestion kinetics and further impact on the release and bioaccessibility of fortified curcumin. So to understand this, we usually use the INFOGEST protocol, and further we use the human gastric simulator to see how dynamics of gastric can contractions can change the structures of the food within the stomach. So the human gastric simulator is one of the machine. We use the dynamic processing in which there are rollers installed that provide the contractions, and we use some titration machine to gradually add the enzyme and simulated fluid. So if you can see this video that clearly shows how the milk is disintegrating within the stomach. So these pipes over there, they are providing enzyme and the assimilated gastric fluid. The rollers are providing the contraction, and how uh, the milk is changing its phase from the liquid to the semi-solid curd. Starting with the coagulation behavior of the dairy gels in the AGS. So what happened? We introduce our gel after the oral phase, and we stop the digestion process of the within the HES after 20 minutes, 60 minutes, 120 minutes, 180 minutes, and 240 minutes. We carried out the digestion for 4 hours, and we took out the curd from the stomach and see how their structure was changing and how the quantity was being reduced over the time. So if you can see in this picture, the ester gel is disintegrating much faster, and even at you can see at the 240 minutes you can find no clot. So most of them was emptied out. But on the other side, the rennet gel, you can see the soft structure transform into the dense curd, and that by the end, even by the end of the gastric phase, like 4 hours, still a lot of the curd particles was staying within the stomach. That shows the rennet gel was comparatively slowly disintegrated. We also performed confocal micrograph of these curd sample, and you can see the acer gel compact curd structure, the protein structure were getting more and open during as the digestion time progressed, while the rennet gel it was disintegrating and it became a bit more compact, and you can see more oil droplet, like columns of oil droplet, more visually appeared by the end of the digestion. Further, in this process, the empty digester that was removed were further characterized for pH changes, which was continuously monitored for after every 20 minutes. Results showed that the rennet gel showed a significantly slower decrease in pH than that was followed by the acer gel. This can be linked with the higher fragmented structure of the curd formed by the rennet gel in the stomach, which further might have ended up with a higher pH buffering. Similarly, when we analyze this digester sample for total solids and oil content, we can see due to the faster disintegration of rennet gel, faster disintegration of acer gel, the more solid content was being passed out and faster emptying rate and compared to the rennet gel. And similarly, pattern we can see the oil content was emptied out at a much faster rate in the acer gel compared to the rennet gel. The free fatty acid release and curcumin bioaccessibility were further analyzed, and the results showed the release of free fatty acid was significantly higher in the gastric digester sample of the acid gel, and the free fatty acid release followed the same pattern to that of the emptying of the oil content in the digester. And the bioaccessibility was relatively higher for the acid gel digester samples, that was around more than 90% for and then for the rennet gel digester samples, the difference in curcumin bioaccessibility can be probably attributed to the compositional and microstructural differences among the gastric digester of the both gels. So from this we can conclude that gel underwent faster disintegration under gastric phase compared to the rennet gel. The restructuring curve formed by the rennet gel in the stomach slowed down the release of lipid and protein in the digester. Because of these structural changes of the milk in the stomach, the composition of gastric digester changed, affecting the free fatty acid release and curcumin bioaccessibility in the small intestine. Coming toward the second topic that we will be discussing with the starch gels. So in this study we use the cornstarch, and cornstarch is generally characterized into three different forms, like waxy cornstarch, the native cornstarch, and high amylose cornstarch. We usually call native cornstarch as a normal cornstarch as well. So why they are different? The reason behind their differences are their different amylose to amylopectin ratio. So usually the waxy cornstarches are contain 0% amylose, and mostly they are 100% amylopectin. So for the native cornstarch, amylose is around 25% and the remaining 75% is amylopectin. And further, the amylose, high amylose cornstarches, they have amylose content of about 70%. Because of their variation in amylose to amylopectin ratio, they usually they are used in food product manufacturing which have different characteristics and structure. Previously, studies have been done on analyzing how waxy normal cornstarch and high malose cornstarch behave, especially the starches with different amylose to amylopectin ratio. They usually give starches having a different textures and then when they are digested, and the starch digestion and glycemic index response is evaluated. So especially the amylose is basically not digestible, so its glycemic index will be low, and mylopectin, it will be on the higher side when the higher glycemic index will be. So based on this, we our hypothesis was that how do gels with different amylopectin and amylose ratio can impact on the release of curcumin. To analyze this, our experimental approach was we used the same technique like we prepared curcumin nanoemulsion using the same methodology as I have previously discussed in the dairy gel sections. And further, we use the same curcumin nanoemulsion, mix it with a starch and water, and then poured them into a tube, and the tube was placed into the hot water bath that was maintained at 95 degrees centigrade for 30 minutes to produce the starches. So these starches usually contain starch around 25% and lipid around 5%. Further, these starches were further introduced for oral and dynamic gastric digestion. The sample that was introduced was around 200 grams. The sample was orally mixed with the salivary fluids for 2 minutes, and then the gastric phase was carried out for 4 hours. And especially the gastric digesta leaving was further subjected to static intestinal digestion. So the gastric digesta leaving at 20 minutes, 120 minutes and 240 minutes for subjected for 2 hours of intestinal digestion. And then after the intestinal digestion, the curcumin bioaccessibility of the digesta sample from coming from the different starches was evaluated. If you see, all the gels containing curcumin nanoemulsion had different textures. Like if you see these gels, the waxy cornstarch was more like a slimy appearance and glossy appearance, but native cornstarch was more compact, while the high amylose cornstarch was more coarse. If we also analyze these gel particle under the scanning electron microscope, and that gave us a very good representation of these gels molecular arrangement. All the gels containing curcumin nanoemulsion had a nodular appearance. You can see all these gel structure, they have some sort of nodular appearance. So Vexicon gels had a continuous and homogeneous structure of the gels like network with the solubilized amylopectin, where the microstructure of the native cornstarch gels confirmed that the non-uniform surface, showing that the environment of amylose granules filled into the almost intact amylopectin network. However, in contrast, the high amylose cornstarch gels differed significantly. The CNE can be, the curcumin emulsion can be seen be embedded into the solubilized amylopectin layer surrounding only the surface of the swollen amylose granules, which may have prevented both the CNE, the curcumin emulsion, and further the amylose crystalline structure from contributing to the gel strength. Starting with the results section of the gastric phase, integration behavior of the starches in the human gastric simulator can be seen in this figure. The visual changes in the structures during the dynamic phase, the digestion was stopped at selected time points like 20 minutes, 120 minutes and 240 minutes, and the gel was separated from the liquid fraction to see how the structures are changing within the stomach. If you see here, the Vexicon starch and gels appear to be uh, slimy at all time points, but its adhesiveness appear to be slightly reduced as the digestion progress. In contrast, the structures of native cornstarch gels and high malose cornstarch gels change significantly during the gastric digestion. At 20 minutes, native cornstarch gels fragments transform into meshy paste, whereas the high malose cornstarch gels appear to be lumpy paste. Further, the wet weight of the gels was analyzed, and you can see from the figure as well, during the digestion from 20 minutes to 240 minutes, most of the waxy cornstarch gel was being retained within the stomach, and while that was followed by the native cornstarch gel and high malose starch. That shows that the high malose cornstarch gel disintegrated much faster within the stomach and emptied out at a faster rate as compared to the other two gels. Further, the confocal micrographs shows that the waxy cornstarch gel, there was not much penetration of gastric fluid, and the structures are almost similar. There was no variation, but on the other side, normal cornstarch and high malose cornstarch gels, the gastric fluid penetrated, and you can see there is a lot of changes in the droplet size variation. The droplet size has been increased. The changes in dry weight and fat content in the digester was also analyzed, and if you can see here, that also commit that what was changing, what the changes happening within the stomach were complementing our these results, that the total solid that emptied out in the digester was faster for the high malose cornstarch gels, followed by native cornstarch gel, and finally with the uh, uh, with the waxy cornstarch gels. Similarly, the oil content that was being emptied out was faster for native corn and high malose cornstarch gel, but by the end, most of the digester was already passed out by the native and high malose starch gels. So the waxy cornstarch gels had a slightly higher at the end, because still there was a lot of gel fragments staying within the stomach. Further, these digester samples emptied at 21, 20 and 240 minutes were further analyzed for starch hydrolysis during the intestinal digestion. So, waxy gel displayed a lowest glucose release for 20-minute sample. This was probably due to the difference in gel breakdown in the oral phase and the stomach chamber. Even though the high malose cornstarch digester fragments released more glucose from the 20-minute sample during the intestinal digestion, its rate of starch hydrolysis was the slowest. Further, at 120 minutes and 240 minutes, the sample's amount of glucose released from the digester sample reduced, which correspond to the changes in the total solid content, that are responding to the compositional changes within the digester. Finally, free fatty acid release and curcumin bioaccessibility of these gels digester sample were analyzed, and there was a high release of free fatty acid in the sample emptying at 20 minutes of the gastric phase, which was followed by the emptying of 120 minutes, 240 minutes of all three starch systems. This matched the compositional difference in the digester sample caused by the changes in the gel under dynamic gastric condition, and then the bioaccessibility. The curcumin incorporated in the various constructs was examined, and the results showed that more than 80% of curcumin was bioaccessible, but the, the fraction of curcumin bioaccessible followed the similar trend to the compositional changes this digester sample had. Finally, during this study, under the dynamic gastric condition, the waxy gel disintegrated and emptied at much lower rate than the native and high amylose cornstarch gels. Despite of the differences in the amylose content of the gel, glucose release was similar due to the differences in the emptying rate of total solid from the gastric simulator. These differences in the digestion behavior of the gel led to allow change the rate of free fatty acid release and the delivery of curcumin in the intestinal digestion phase. So out of this those studies, we have published two articles in our very reputable food journals. Further, we have recently published a review article in Critical Reviews and Food Science and Nutrition. This review explores recent advancement in using food matrices for delivery of bioactive compound, focusing on encapsulating techniques, stability, and bioavailability. Finally, I would like to thank my supervisor for their continuous guidance and support, and also like to thank the Riddet Institute and Higher Education Commission of Pakistan for the research support and funding they have provided me. And finally, I will thank everyone for listening me. And here is my email address. If someone has queries, they can reach out to me, and I'm happy to answer everyone's question now. Thank you very much.
Thank you, Haroon, for your very nice presentation. Now we can continue with the Q&A section. So the first question that we have for you is, why did you choose curcumin, and in what type of foods are these gels intended to be incorporated?
Curcumin was basically one of the example that we were trying to find out some lipophilic active compounds, and we wanted to evaluate that how one of the bioactive compound, like any type of lipophilic bioactive compound, can interact within the food matrix. Actually, our main plan was to see how the different food matrix disintegrate and how do they impact on any type of mostly we are trying to prepare these days like different type of pills or nutraceuticals, but most of the studies lack uh, incorporate them in the food. We wanted to see how the food matrix basically impact the release of those bioactive compounds. So curcumin was just an example. And talking about the food matrix, we basically decided like in mostly the Asian countries, curcumin basically is extracted from the turmeric powder, and turmeric is basically added as an anti-inflammatory, and usually they are when it is mostly added into the heated milk, and people usually consume to get relief from any sort of soreness in their muscles. So that idea clicked me, and so that I try to work with the curcumin in my study.
We have another one. Do you think that the presence of curcumin has an impact on the digestive behavior?
No, I don't think so, because cumin basically generally considered as a indicator like of a pH sensitive, because as the pH turns most alkaline, so its color changes to red. So definitely it degrades. But the other thing is that because usually the environment in our gut is around acidic, and uh, in our small intestine is nearly neutral. So uh, it doesn't have an impact. But the thing is that most of the curcumin, that the studies have shown that most of the curcumin that we consume without any delivery system usually don't get absorbed, and usually it mostly pass out of the body in the feces. So that's the reason we really encapsulated them, so that nanoemulsion has previously shown quite promising. Like it's a promising technique that it can increase the bioaccessibility of those of any bioactive compound. So curcumin, like it was like only one example, but during this environment, it didn't have any interaction within the system, but definitely it followed the similar pattern how the food product were disintegrating. And because curcumin is mostly lipid soluble, so uh, it followed a similar pattern how the lipid was being emptied out from the food matrix.
Okay, thank you. I think our third question is related with a bit with the last answer. Do you think that the composition of the starch has an effect on the bioaccessibility of curcumin? Is there any kind of interaction between amylose and curcumin, or are the differences only due to the different textures?
Uh, we didn't went into analyzing the interaction of these amylose and amylopectin with the curcumin, because curcumin was already encapsulated using sodium caseinate. And but when we performed some SEM analysis, and we saw that uh, during the gelation of these starches, uh, these nanoemulsions were interacting in a different pattern. So especially when you can see the presentation when you saw that mostly the high amylose cornstarch gels, they didn't gelatinize completely. So you can see the amylose granules still intact, and only the amylose pectin that was gelatinized, that formed a surface like a surface around those granules, and these uh, curcumin nanoemulsions for entrapped on those gelatinized surface. So definitely, we have seen that introduction of introducing these curcumin nanoemulsion into the gel, they really impact on the structural properties of the gel. We already performed some analysis, like we prepared some gels without emulsions and with emulsion, and definitely they really change the storage modulus of these gels, and definitely they will be having an impact. We saw that they have an impact on the structural and how they change, and how they further behave in the gastric digestion.
Okay, thank you.
I think we have more questions. The first question from the chat is from Deepak. So in the context of more plant-based products, cheese, yogurt in market, can you describe how this knowledge on digestion and release of curcumin nanoemulsion in dairy matrix and starch matrix can be extended to plant protein and starch-based combined matrices?
It's an interesting question. So definitely, when the plant, we have recently been working with different plant-based milks in our lab, and we have worked with some plant-based cheeses as well. So definitely, when all those protein matrices, they will have a different disintegration behavior within the gut, and definitely over the time, when the changes when in the stomach, when the changes are happening gradually, and the digesta is coming out slowly, so definitely how those protein or starch matrices will interact with each other and during the processing will have an impact during the digestion within the gut, and especially in the stomach, how they disintegrate, how the protein coagulates or again restructure within the stomach, will impact on the disintegration and the release of and the composition of the gastric digester leaving the stomach, and that will further impact on the bioaccessibility of any fortified bioactive compound.
Okay, thank you so much. I think we have more questions. This question is from Mary Lena. So it's, why did you choose gels and not another structure?
No, we initially started working with the recombined milk systems. We initially worked with the skim milk powder that was initially differently heated. Like we have like a low heated skim milk powder, medium heated, and high heated. And the heat basically changed the structure WPNI values of these milk powders. So as a higher heated milk powder disintegrate much faster as compared to the low heated. So especially the high heated milk powders are mostly used in the confectionery industries, and the low heated are morely recommended for the cheese processing. So definitely we were intentionally dealing with that initially milk. How do they disintegrate? And similarly, my supervisor previously we have worked with different type of milk systems as well, like milk from different species, like deer milk, goat milk, cow milk, how they disintegrate, and especially how the raw milk structure the clot in the stomach, and compared to homogenized milk or pasteurized milk and UHT milk. So as we heat the milk, the protein denatures, and definitely they form a different structure clot. Especially if I talk about the raw milk, it form a very compact structured clot into the stomach, and it really takes a longer time to empty from the stomach as compared to the high heated milk. It form a very crumbly structure curd that disintegrate much faster and leave the stomach at a much faster rate. We already published this study in Frontier in Nutrition, so I think you can search that online.
Okay. I think there is another question here. Uh, this study only seems to refer to bioaccessibility. Were any studies performed on bioavailability?
We initially planned to go for the bioavailability and perform some animal trials. We have worked with some of the food matrix without any fortified compound. We have worked with different milk systems, and we have done some pig trials and seen the similarities. What we are seeing in the human gastric simulator, we saw the similar things happening in the pigs as well. Similarly, my friend and my colleague Joanna Nadia, she also worked with the starch with different matrices and see how the starch is being impacting in the HES as well and in the pig models. So I think we were trying to replicate how the things are in human stomach when not everything happens like a static model, because in the static model we usually add all the enzyme all together, and usually it provides the end product. So we want to see how the dynamics in between the digestion time, how these are changing the food matrices restructuring, and how those restructuring basically impact on the release of those compounds.
Okay. I think we don't have more questions. So thank you so much, Haroon, for the discussion, for your presentation, and for everything.
You are welcome.
So now I'm gonna share my screen. So for the next webinars, we will have Cahal Dole from Teagasc, Ireland, the next February the 5th, and then we will have Connor Fitzpatrick in March webinar, and then we will have Doreen Jens from KU Leuven, Belgium, on the webinar in April. So we are actually still trying to find speakers. We have available position for June, July, and August. So if you are interested, if you want to present and use this platform to disseminate your results, just send us an email and reach out with us. And I think that's it. So thank you for your attendance, and see you on the next webinar in February. Bye-bye.